Alright, welcome back. Today we have text problem 29-49 for lesson 37. As always, get a scratch piece of paper out or a blank printout of the problem so you can follow along as I will routinely ask you to pause the video and work ahead a few steps before you pick back up again to check your work. Alright, first step, the read step. Go ahead and read the problem. And when I go through this, I see that we have a toroid. It is a square cross-section. It gives me the dimensions of each of our sides. And it gives me an inner radius. And let's see, the number of turns and the current going through it. So I know I'm going to have a Ampere's law. And I know I have a toroid. And the square cross section is going to more play into our draw step. But the Ampere's law will take care of our actual task of calculating the magnetic field at the inner radius and the outside radius. And because we have a toroid, that will help us pick the correct magnetic field equation to solve for. Alright, so let's get to the draw step. First off, we don't need that. So looks like they took some picture from the book and just tried to replicate it, but really we've got something more along the lines of this, where in this instance we have our square cross section, and then we have our wire coiled around that, and to give us a flow or direction of our current, we have it going into the screen on the left side and out of the screen on the right side. So we can see that circling around over and over and over, and it's that coil, even though it's in a square cross section, that is going to provide that magnetic field inside our toroid. Now, we take what we have shown here, because this is essentially a solenoid. It's not a toroid until we take our square cross-section and bend it around into a circle, creating a donut shape, just like it says in the problem. So let's see what that looks like. So now I have a toroid here next to our square. So here's our toroid. The inner and outer circle, remember, it is a square cross-section, and then we've bent it around into a circle. So our current comes in here on the left side, goes around our square cross-section, all the way around our circle, and then out here on the right side. Now, because I have a toroid, I have an inner radius, little r, and an outer radius, big R. We know what big R is based off of the given inner radius value and our square cross section. So our inner radius is going to be 15 centimeters and our outer radius is going to be 20 centimeters. And that pretty much leads right into our given step. In addition to our dimensions here, we were also given the current through our toroid and the number of turns in our toroid. Alright, so let's move on to our assumption step. We're going to need some more room. We're going to assume we have an ideal toroid. That is because we want to assume that all of the magnetic field is inside of our coil, so inside that square cross-section as we bend it around into a circle. Anything outside of our toroid, the magnetic field is going to be equal to 0. That means anything less than small r or bigger than big R. Alright, so that's what that ideal toroid means. Now, as we move on to our task step, so our first task is to calculate the magnetic field at the inner radius of our toroid, and our second task is to calculate the magnetic field at the outer radius. Notice that it doesn't specifically say calculate the magnitude of the magnetic field. Just the magnetic field. That means we're going to need to provide some direction information to our magnitude quantity. Alright, so you are given the equation for the magnitude of the magnetic field inside of a toroid on your PRC, but not the direction information. And, well, we'll get to that later, how we're going to figure that out. Alright, so moving on. Next we have our physics step. I want you to pause the video and write down the equation you think you will need to calculate the magnetic field inside the toroid. Alright, so I will see you here in a minute. Alright, so here's the equation we will need to calculate the magnitude of the magnetic field inside our toroid, where this value, little r, is the distance from the center of our donut to any position inside of our toroid. Okay? Not out here, not inside here, only in our circular portion of the toroid. Okay. Alright, now that we have our physics step taken care of, we can move on to the solve step. Alright, so we have the strength of our magnetic field. I want you all to take a second, substitute the values for part A into our equation, and see how you do. Alright, so we put in our value for the permeability of free space. We put in our current, the number of turns in our toroid, and the distance from the center of our circular donut to the inside radius of our toroid, which is 15 centimeters. We convert that to meters because meters are the SI unit for any distance measurement. Alright? So that's one of the key factors in substituting in values. Convert those units, or the number, so that it represents the measurement in SI units. Okay, so the answer we get is 533 times 10 to the negative 6 Teslas, or you could say 533 micro Tesla. Alright. Now, that gives us the magnitude, but does it give us our direction? So, we can use the right-hand rule to give us the direction of the magnetic field inside the toroid. So, we use our right hand. Let's see if I can insert a picture here. Stand by. So here I have a picture of my right hand, and it's like I am grabbing the wire with my right hand with my thumb in the direction of the current. As my fingers wrap around that wire, my fingers themselves point in the direction of the magnetic field. So as the picture shows, if the current is going up in the direction of my thumb, then the magnetic field, in this case, is coming out of the screen. As I continue to wrap my fingers around that wire all the way, on the right-hand side of the wire, I will have the magnetic field pointing into the page. So let me see if I can represent that. On the right-hand side of the wire, I have the magnetic field going into the page. Now, if we apply this rule to our toroid, let's look at the current coming out of the toroid, the lead on the right-hand side at the top. Since our hand, or my hand, is already in the orientation of our diagram, then we can see that the magnetic field, since the lead is on the bottom of our square cross-section toroid, is pointing to the right. Now, as we go and look at the lead on the other side, where the current is coming into the toroid, then I would flip my hand over, so my thumb is pointing down, and see how the wire crosses over the toroid, or the cross-section, the square cross-section? In that case, the magnetic field inside the toroid would still be pointing to the right. And so we end up getting, let's see if I can change my color here to something different. The magnetic field inside the toroid is traveling in a clockwise direction. Okay? So we applied our right-hand rule to give us the direction of the magnetic field. This right-hand rule applies to straight wires, all kinds of wires in any direction. It just so happens that we apply our right-hand rule to the wire at a specific point on that square cross-section. So the first time I said with the current going out, the wire is on the bottom, and so our palm is facing us. But in the case where the current is coming in, the wire goes over the top of the toroid, and so our palm is facing away from us. That magnetic field is going into and out of the page. Right over the top of the wire, it's pointing to the right, and below the wire, it's pointing to the left. Okay. All right, so if you have questions about this, ask me in class, or if you're not in my class, ask your teacher. They will be more than happy to explain the right-hand rule as it applies to the direction of the magnetic field to a current carrying wire. Alright, that covers part A. I want you to pause the video and do part B. Now for part B, the only difference from part A is the fact that we're now looking at the strength of the magnetic field at the outer radius of our toroid, and in this case we end up with 400. Now notice that for significant figure purposes, the dot here at the end of 400 means that, of course, the 4 is significant, but as are both our zeros. So that's what that dot represents. And again, we have microtesla, or times 10 to the negative 6 teslas, and it's moving in a counterclockwise direction. So that gives us both our magnitude and direction. So these are vector quantities, not just magnitudes. All right. Now the reason that the strength of the magnetic field is different on the inside than it is from the outside is because in a long straight solenoid or coil, which is a solenoid, we have a uniform magnetic field on the inside. When we take that long straight coil and bend it around into a circle, on the inside there's more of that magnetic field compressed into a smaller portion than we have on the outside. It's no different than taking a map of the world and taking the globe and putting it onto a 2D surface. Some of the edges get stretched more than some of the places along the equator. Or when you are driving around a corner, if you didn't have a beautiful differential inside of your axle, then your wheels would actually be burning rubber as you go around a corner. That's because the inside tire is not moving as far as the outside tire is. So you have a difference between those because of the curve path that you were taking. Okay, that's it more or less for this problem. I think I might try to do a theoretical approach to to deriving the magnetic fields for each of the different geometries, but I'll have that as a separate video. Alright, thanks for stopping by, and as we close on this semester, I hope you are studying. Alright, that's it. See you in class. And we can't forget the old-fashioned cuteness tax.